vector exploration activity that we did in class together, you explored this website here, Vector Addition, phet.colorado.edu. They have some great sims there. And played around with this thing called a vector that seems to have sort of a starting point and an ending point, an arrow that indicates that it has direction more than just being the hypotenuse, right? So as we look at these numbers, we see there's a 20 here, and it's labeled a sub x up here is the same value, 20. As I change this around, the a sub x matches what they're labeling here along the x direction. And the a sub y seems to match this vertical end. Many of you called that a sub x the adjacent side of the triangle. But I want you to know that in this context, we're going to call it the x component, and that will be formalized in class tomorrow. And then a sub y would have been the opposite, which is true. In where theta is labeled, theta seems to match, see the theta up here, seems to match the theta down here from the horizontal axis. The opposite side would also be, and now we're going to call it the y component of the vector. So theta then represents the angle of interest, but specifically in vector terminology, it'll be the sort of the angle of inclination or angle of elevation from the positive x-axis. I want you to notice something that you may not have done is when you rotate the vector out here, it's still measuring that angle from the positive x-axis. And when we go past 180, it starts to measure it in sort of a negative way. Now we have a negative angle, which is kind of weird, but it's also taking it from that positive x-axis. When we aim our vector horizontally, it says that the angle is 0. So it's the angle from the positive x-axis is what I was going for on that. Please don't erase your answers and replace them with mine. I want you to have both of those ideas out there because you did this exploration and your observations are perfectly valid. I'm just adding the vector notation or verbiage, vocabulary, to what you've already done. So what does this absolute value of a thing look like, right? It's got these bars along either side. Well, notice that even as the angle goes negative or the x and y components go negative, this still stays positive. So that absolute value isn't far off. You might have also called it the hypotenuse, which is totally valid. You would have used complete sentences, by the way. But we're going to call it the magnitude. The magnitude, or which is the same as the length of the vector. But magnitude is the official word there, just like x component and y component are the official words. There you go. We actually might call theta our direction. Let's call it the direction of the vector. So why does it have an arrowhead? It's not a ray. It doesn't mean it goes on forever because we just determined that it has a fixed length. But that does sort of indicate that it has a favorite, right? So even if we bring it over here and make the same arrow, connect the points 0 with the point 12, 8, if we change it up over here to 12, 8, and move it back in the same spot, it's the same segment, but it's pointing a different direction. And so that arrowhead tells you that it has a start and a finish. A tail and a head, which we later described. So when we reshape the A vector to be completely horizontal, reshape the V vector, we start to see something like this. If you followed the directions, you'd look something like this, but your vectors would be shorter because you were supposed to be with less than 10. And the sum, when I click this sum, it may have appeared somewhere up here, but we would drag it down to start at the beginning of A and end at the end of B. And it appears that if you followed the path from along A and then along B, you would get to the same point as if you started at the base of S, the tail of S, and went to the head or tip of S. So S is the sum, as it says, of A plus B. You might also notice that we have created ourselves a right triangle. You can see this angle is labeled 90. And this angle is down here. I can't quite see what it is, 33.7. Oh yeah, it's also labeled up here. So we could use all of our trig SOHCAHTOA stuff on this. We could also use the Pythagorean theorem on this. Either one of those is only applicable to right triangles, though. So it's important to note that only when one vector is horizontal and one is vertical can we use the Pythagorean theorem on those to calculate the magnitude of the sum. Or can we use SOHCAHTOA to explore using the angle that we know the various relationships among the sides. So I'm going to click off my sum and throw away my A and B, bring out my C. Now you were supposed to make your C have a value of something between 0 and 12, but I'm going to make mine really big just for fun. And but it doesn't matter. I can see if I've clicked this button right here, right? If you don't see this, it's because you didn't click this button right here. I can see that my X component, my C sub X is 22, my Y component is 10, and that gets me to this point here where my magnitude is 24.2, and my angle, if I did inverse tan of opposite over adjacent, I would find that the angle is 24.4. And it doesn't seem to matter where I put it. So when you drag yours up to have its tip or tail at 2515 or whatever I told you to do, it doesn't change the values of up here, these descriptive values of vector C. It doesn't matter where it is, it has a beginning and an end and a relationship between them that can be any given point. So that leads me down to the imagine. Imagine that your C vector represents a composite translation. Imagine I had a shape that I drew right here, and if I use this vector C to describe that transformation from the pre-image to the image, right, I can see that I would go to the right by 22 and then up by 10 for each of these points. Even from down here, if I went to the right by 22 and then up by 10, I would find myself in the same place. So these components add to this composite vector, just like two back-to-back, a horizontal and a vertical translation, add to a diagonal translation. So what I'm looking for then here is something along the lines of x plus 22. In my case, I went horizontal 22 in the positive direction, and then y plus, what did I have, 10? Yeah, plus 10. So my pre-image points, one of the vertices of my shape perhaps, would go to my image point of 27. 5 plus 22, and 6 plus 10 is 16. So my pre-image would become my image by translating in that way, in a composite fashion. Imagine now that C vector represents how hard you are pulling the handle of a wagon that will roll across the floor. So another image would be in order here. If we can draw a picture of a wagon, and then we pull that wagon at an angle from the horizontal, right? How hard you're pulling the handle of a wagon that will roll across the floor. Since you aren't lifting the wagon, right, lifting would be the Y component, they're asking how much of your pulling is actually causing the wagon to roll forward or in the X direction. So if I can change my color here, they're looking for what part of your C vector is actually causing motion in this direction, right? Remember, this was my C vector, so this is my C sub X. That is the component of the vector in the horizontal direction. Because my C sub Y is just, you know, trying to lift the wagon up off the ground. It's probably not more than the weight of the wagon, but, right? So C sub x is really the answer here, but specifically your C sub x. In my case, it would be 22, the component of my particular C vector in the horizontal direction. So you give yours. And then in general, if you know the length of a horizontal part of a vector, so again, draw a picture. If I know the length of the horizontal component of a vector, and you know the length of the vertical component of a vector, how can you find the magnitude of the vector? The magnitude being the overall length of the vector itself. Its absolute value of C, right, of the C vector. Well, that's the hypotenuse of a right triangle, right? Remember, this is a right triangle because these components are in the x and y directions, which are perpendicular. Then, indeed, it's going to be the Pythagorean theorem. So, what do you think? If I wanted to compose a translation by a vector A that goes right up, so here's the deal. I'm going to draw A. It goes right by 2 and up by 5. Got a horizontal component of positive 2 and a vertical component of 5. That's my A vector. But then also go 4 to the right and down by 1. Right? So these are the directions I'm following. I'm going to the right by 2, up by 5, then to the right by 4, and then down by 1. So my B vector, which maybe I should have done in a different color, but I'm not very good at this art thing. My B vector takes me a little bit back, right? So this is -1, and this is a positive 4. So how much in total? What is my composite or final from the beginning, the start point, to the end point? Notice that I put all these vectors tip to tail like I asked you to do for A plus B in the very first couple of activities. This C vector is the A vector plus the B vector, and what I'm really saying is that C has a horizontal component of 2 plus 4 of 6. C has a horizontal component of 6 and a vertical component of 5 minus 1, so 4. So my final translation, if I wanted to put it in coordinate notation, would be x plus 6 and y plus 4. But my C vector's name is just 6, 4. It just goes over by 6 and up by 4. All right, we'll formalize this in class, but hope that helps you understand where I was going with some of this and maybe start to use the language.